Hello, welcome back on another Botanical Garden Day. There's one handout today, which are some lecture notes and a couple of papers that I think it would be useful for you to read. People who are native Californians don't really appreciate how wonderful it is to have days like this in February. It's incredible. I brought in another toy from my historical collection at home. Does anybody want to guess as to what this thing might be? It's got connectors and kind of leaves. It's memory of a kind. Yeah, what kind of memory?
Read-only memory.
Read-only memory. You got it. This is actually a microprogram. This is a microprogram for an I/O computer that IBM built in the mid-60s, I guess, something like that. And they had to have a way of storing the microprogram. We'll talk a little bit about microprogramming a little bit later, in a way that was easily replaced in the field. So in fact, the program is stored on these sort of mylar strips on which are printed loops around each one of these cores. And carefully punched, interrupting the loop in one direction or the other, are some holes in the mylar strips. So the current either flows clockwise or counterclockwise around each little core, depending on whether that bit is supposed to be a 0 or a 1. And in fact, you could replace the entire unit if you wanted to change the microprogram, or you could take out one of these little strips, and that represents one word. Each one of those strips represents a 48-bit word for a 48-bit wide instruction computer. I'll pass this around for you to amuse yourself with. It's actually interesting that people have had to be much more clever in the design of memories, or at least much more imaginative in the design of memories than in the design of logic. Logic was originally designed with, well, I guess relays if you go back far enough, but vacuum tubes after that, and then transistors. And ever since, it's just been transistors and more transistors. But memories have come in an incredible variety of forms. Core memories, in fact, next time I'll bring in an example of a core memory, which was sort of the old standby for computers for a long time for random access memories. But there were a variety of bizarre technologies used for memories when it was much too expensive to build them out of the same logic that you build ALUs out of. You couldn't afford to build memories out of vacuum tubes because you just need too many of them. You already needed too many of them just to do the logic. So there were things like CRTs. You could store a bit on a position on the screen of a CRT called the Williams tube in those days, and the phosphor would glow and cause emission of electrons if it were excited with another beam. So you could basically store 1,000 bits on the front screen of a CRT and be able to read it back from within the tube. Another popular technique were delay lines. In fact, IBM, it may have even have been the machine that had that as a read-only memory, had as a random access memory a tube filled with a liquid like mercury. And you would tap the mercury at one end, and after some delay, the taps would filter through in a pipeline sense and come out the other end of the delay line. So that delay line could store 100 bits or 200 bits of information, and that could be the main memory for a computer. Serial and hard to access, but in fact that was used for communication controllers where you didn't have to get random access, but a shift register-like scheme was just fine. There were lots of computers that didn't have electronic main memory at all. They had magnetic disk. Well, the magnetic disk main memories like the IBM 650 that I talked about originally, where there was no random access main memory. Everything was on the drum or the disk, and that was the way programs were fetched and executed one word at a time. So in some ways, the history of memory architectures is much more interesting than the history of logic implementations, but be that as it may. Does Stanford have a course in the history of computers? Seems like they ought to. That would be an interesting thing to do. Last time we talked about making branches faster. And just before I leave that, I wanted to make sure that you're comfortable with doing these kind of back-of-the-envelope conditional probability calculations that you need to do to get an estimate of performance. Remember last time we talked about branch target buffers, and the clever thing about branch target buffers is that if you do it in instruction fetch, when you're fetching the instruction, you can look up the target address that instruction will go to if it just happens to be a branch. So in fact, you can get a zero penalty for taken branches. If that's the case, let's try to compute what the penalty might be for a branch target buffer in various cases. So the branch target buffer penalty is, well, one case is that we may hit. So a certain percentage of the time we hit in the buffer, we discover that it's a branch. And sometimes we're right and sometimes we're wrong. So a certain percentage of the time that we hit, we're right. And to compute the penalty, we multiply by the penalty when in fact we're right. Now for us, because we did it in instruction fetch, the penalty is in fact 0, but it might not be. Another percentage of the time we might be wrong, even though it hit in the cache, and there is a penalty associated with that. And in fact, for us, because that's discovered after ID, the wrong penalty is 2 cycles. Now that is the case where we hit in the cache. There's now the case where we missed in the cache, so we have to multiply by some miss penalty where the cache didn't hit. But here again, there are a couple of different cases, because if it's not in the cache, then we can revert back to the original scheme we had before and predict the branch based on whether we think it's going to be taken or not taken. So we can compute the miss penalty as the percentage of time that the branch is taken times the taken penalty plus the percentage of time that it's not taken times the not taken penalty. I'm abbreviating here because I'm running out of space on the pad. And for us, if we're predicting not taken, then the not taken penalty is 0, and the taken penalty is 2. So let's make up some numbers and see roughly what kind of penalty the branch target buffer gives us and how much better it is than not doing it. Let's assume that the percentage of time that we hit in the cache is 90%. And of those times, the percentage of time that we're right is also 90%. The other thing we need to know is that the percentage of time that the branch is taken for those cases where we're not hitting and we need to compute the miss penalty, let's say that 65% of the branches are taken. So the miss penalty is the percentage of time taken times the taken penalty, which is 65% of 2, plus no penalty for the case where it's not taken. So in our case, the miss penalty, which is what it would cost us if we didn't do any branch target buffer at all, is 1.3 cycles. But we do have the branch target buffer, or if we do, and in that case the penalty is the percentage of time we hit, which is 0.9, times the percentage of time that it's right, which is also 0.9. I'm sorry, the percentage of time that it's wrong. The percentage of time is right is 0.9, but it doesn't matter because the right penalty is 0. The percentage of time that it's wrong is 0.1, and that's the case where we pay the 2 penalty delay. So, and then add to that the percentage of miss, which is 0.1, times the miss penalty, which is 1.3. So the total is 0.18 plus 0.13, or 0.31 cycles. Compared to, without the branch target buffer, 1.3 cycles. So we basically shaved an entire cycle off the penalty for branches. Simple conditional probability calculations, but it gives you a rough order of magnitude estimation of whether or not these structures are a good idea and how good they are. Any questions about that? Okay. let us leave behind branches, and now we're going to start to talk about how we can do even better. What we've got so far with our machine is a pipeline machine where if we're doing really well, we can get down to very close to 1 cycle per instruction. And the last hard problem was getting branches to work right, and with branch target buffers of appropriate size and cleverness, we can reduce the penalty there to fractions of a cycle and do really well. So how can we do better? Well, one way we can do better is by, in fact, trying to execute and issue multiple instructions at one time. We've already been, with some of this dynamic scheduling techniques, been executing multiple instructions at a time, and in fact executing them out of order. But the idea now is to try to issue multiple instructions in each cycle. Rather than starting 1 instruction per cycle, start multiple instructions in each cycle. Well, there are basically 2 ways to do it. One way is to give up on our RISC-like instruction set architecture, or at least the one we've been looking at, and change the instruction set architecture so that the compiler, in fact, can bundle together instructions that can be issued at the same time into one very wide word instruction, and that's called VLIW, a very long instruction word machine. Microprogrammed machines, in fact, like that memory that's going around there, typically were VLIW machines. They had very wide instructions, packed lots of individual operations in them, and it was the compiler, or in that case, the programmer's responsibility to pack them together in a way that they could all be issued at the same time. And we'll look at how VLIW machines look these days. The other approach is to stick with our current instruction set architecture and figure out some way to in 1 cycle, in fact, issue multiple instructions. And these are the so-called superscalar pipelines, of which there are a wide variety. It's the hottest thing these days. All of the companies are announcing or have shipped superscalar microprocessors. You can do it in a simple fashion. We'll look at the 21064 in great detail, where you issue multiple instructions at once, but you execute them in order in a kind of traditional pipeline. You can issue multiple instructions at once and then combine that with some of the dynamic scheduling stuff we've been doing so that you can execute them out of order. And you can do even more than that. You can, in fact, execute beyond branches before you even know which way the branch is going to go, not just fetching beyond the branch, but actually executing beyond the branch, and that's called speculative execution. And we'll look in detail at the PowerPC 604, which is the first microprocessor to do speculative execution. So the idea is to issue a bunch of instructions in 1 cycle. Sort of 1 to 8 is the limit or 2 to 8 is the limit of what reasonably can be achieved. But there are a number of constraints because there may be limited functional units, there may be ordering constraints having to do with hazards, like read after write hazards, or some other hazards if we don't have the appropriate renaming. And we'll see in detail how these limitations restrict the number of issues per cycle that you can actually achieve. But let's first look at VLIW, this very long instruction word. Well, I said make the instruction big, and in fact you can make instructions 200 bits or more. In fact, I'll give one example of a machine which had 1,000 bits in an instruction. But if you have 200 bits, then you can pack, let's say, 8 or 10 RISC-like instructions per each one of these words. Now, this is either an advantage or a disadvantage, depending on whether you're a compiler writer or a hardware designer. The checks, the dependencies to make sure that all of those instruction fragments that can be issued at the same time are not done at execution time. They're done at compile time. The compiler has to know a great deal about the internal organization of the machine to know that there aren't resource conflicts with 2 things that it's assigning to different parts of this very long word, that there aren't any dependencies, and so forth. One could argue that this is the right time to do it because you've got all the time in the world, and trying to make the hardware do it when it's got 5 or 10 nanoseconds to make a decision is sort of an unfair burden to put on the hardware. But it means that the compilers are very, very specific to particular VLIW instruction sets, and that makes it harder to get a product to market because you've got to have a brand new novel compiler as well as a brand new novel piece of hardware. One of the other disadvantages is that it's not object code compatible. So if you come out with a new version of this computer, obviously your customers' old programs are not going to run. They have to be recompiled, and recompiled with this new compiler that knows all about the new machine. But this is an example of an organization that might do that. You might have a very wide word that allows you to, at one time, do a load and a store, a couple of integer operations, because in fact there are two separate integer ALUs, a couple of floating point operations, and a branch operation, all at the same time. Now notice that lots of these instructions are probably going to want to get to the register file at the same time. These are all being issued in the same cycle, and the pipeline is sort of proceeding down in this direction, and they're all going to be hitting the register file at the same time, so that certainly represents a problem. One of the questions is, how good can this do? Is, in fact, there enough parallelism in most programs in order to take advantage of the multiple issue that a VLIW instruction stream can give you? Well, you need a lot, because if there are, let's say, 6 pipeline stages in your pipeline, and you've got 6 or 7 functional units, then you could keep 20 or 30 independent operations going on at one time. And it's very difficult in most programs to find that level of instruction level parallelism. The book goes through an example of sort of one of the simple loops for a machine that has 7 functional units, and it tries to execute this loop that adds a constant to a vector. And in fact, in order to get maximum throughput, it unrolls the loop enough to make 7 independent copies of the loop in 9 instructions. So basically the loop executes 9 instructions and has executed 7 iterations of that loop. So the efficiency is great, yet even so, in that case, only 60% of the slots are occupied. Here's the picture from the book of, in fact, what those instructions look like. This is a machine, you can focus in only on this center part here, where you can do 2 memory references at once, 2 floating point operations at once, and some integer or branch operation. So in fact, the first 1, 2, 3, 4 instructions issue a total of 7 loads, all simultaneously. And then the adds are sort of stacked up over here, and the stores are stacked up over here, issuing 2 per cycle. And the branch on the last instruction goes back to the beginning, 9 instructions later, but you've done 7 iterations of the loop during that time. But in some sense, the efficiency is only 60%, because you've still got 40% of the slots unused, which means 40% of the instruction bits in your computer are being wasted. So instruction density is an issue for VLIW machines as well. You also need lots of registers. This is equivalent to doing loop unrolling. Well, it is loop unrolling. And in fact, in that trivial example where you really only needed 1 floating point register, if you did it in the trivial sense, you now need 8 floating point registers. It's hard to calculate what the CPI of a machine like this is, because I'm not sure what you count as an instruction. It's unfair to count each VLIW wide word as an instruction. If you look at the operations per cycle, there are on the average 2.5 of them done per cycle. So in some sense, the CPI or CP operation is 0.4. So we've at least in a kind of naive comparison to a standard pipeline machine, gained by a factor of 2 or something like that. But this comes at a cost. Obviously, to make this work, you need lots of functional units, and the die area of a chip is proportional to the number of functional units. So the more you do this, the more space you take, the less space is available for caches and so forth. It's a trade-off. The register file, as I pointed out, needs lots of read-write ports to avoid functional unit stalls or structural hazards trying to read the ports. And register files with lots of ports are typically slower than ones with fewer ports, and they're difficult to design. They take lots of space. And as I mentioned, the code space increases because there are 50% or more of the operations which are now no-ops. So that means that either you try to be clever in encoding, and I'll show a machine that did that, or you wind up wanting to put a bigger cache on your machine, but you've just used up all your die area for additional functional units, so you don't have a lot of space for bigger caches. So VLIW has some advantages, but has lots of disadvantages. It's an idea that keeps coming around. In some sense, VLIW machines were around in the early days because they were the microprogrammed machines. They were the inner computers that executed the instructions for the outer computer, and they were typically wide word machines. In the 1980s, people started building VLIW machines where the VLIW instruction was the only one that was exposed, and in fact was a more classic VLIW machine of the kind I've been describing. Multiflow had one where they had 256-bit instructions, which contained 7 kind of classical 3-operand RISC-like instructions encoded in 32 bits, except that they shared one immediate field, which was off at the end of the word. One of the novel things about this machine was that, in fact, you could gang together multiples of these instructions, and in fact, depending on how many bucks you wanted to send them, you could buy a machine that was either 256 bits wide, or 512 bits wide, or 1024 bits wide, and you would tell the compiler how wide your computer was, or how wide the instruction word was, and it would try to schedule as many as it can in an individual word. In fact, the technology they used for their compiler was probably the greatest success for that company, because their machines weren't much of a success. But in fact, they've gone on to license some of their compiler techniques to other companies. Sidrone was another company that tried to make VLIW machines. One of the clever things about that they did was to recognize that instruction density was a problem, and caches couldn't be made big enough to cover up for it. So in fact, they were a little bit CISC-like in their design of the long instruction word, and they allowed a variable length encoding for the different pieces in the word. The other thing they did was that if you had to punt, which is to say you had one of these, I don't know, 256-bit wide words, and all you could do is one operation that only took you, I don't know, 32 bits or something to encode, and that went on for a while, then in fact there was another format for this long word, which basically represented sequentially issuing normal instructions within one very wide word. Basically, if you fetch one of these 256-bit words, you could look at one bit that says, is this an instruction that's supposed to be executed in parallel with 7 or 8 different operations? Or couldn't I find enough things to do in parallel, and you should execute these things one at a time in sequence, thereby saving a lot of instruction encoding space? That was their great contribution to the VLIW domain. Both of those companies and machines, I believe, are no longer in existence. However, it seems like VLIW is about to come back in another wave, and HP and Philips have both announced plans to build VLIW machines. It's expected that both Intel and IBM will be announcing VLIW machines, so keep your eye on it, because it will be returning, like lots of things in computer architecture. But let's say that we don't want to do that, and instead we want to stick with our instruction set architecture. We want to keep pretty much the same compilers and not give our customers headaches in changing the instruction set design. Let's instead do what we described earlier, which is a superscalar. And let's look first at the sort of best case, the ideal superscalar issue machine. Traditional 5-stage pipeline, but here in fact we're fetching instruction I plus 1 at the same time. We're decoding them both at the same time, executing both at the same time. They all go through all of the stages of pipeline at the same time. One cycle later you fetch another 2 instructions. So if you do this, you can get an ideal CPI of 0.5. You've doubled the execution time of the machine. Well, got some problems, obviously. For one thing, you've just doubled everything that you need to execute in the machine. The register file now has to have twice as many read and write ports as it had before. You have to have twice as many functional units as you had before, under the assumption that there are no restrictions about which instructions get paired up. So you can't have just one floating point unit and one fixed point unit, because this pair might be 2 fixed point instructions. Now, we have all of the same hazards and branch and load delays that we had before, but in fact, they have a worse effect. Because now if we have a load delay of 2, that load delay is 2 cycles, but 2 cycles represents 4 instructions. So in fact, the effect of things like branch and load delays might be a factor of 2 worse than they were before. Might not be that bad. It depends on where in the cycle it is and whether it's the first half of the word or the second half of the word. But in the worst case, you've got to look at these delays and remember that delays are counted in cycles, and in a superscalar machine, cycles may represent multiple instructions. Well, that's the ideal machine. For one thing, it's very expensive to build. How can you reduce the cost? Well, one way is to start removing the hardware, reduce the number of functional units. That introduces structural hazards, so that you are now adding restrictions on the instructions that can be issued in parallel. And all of the superscalar machines have a whole list of restrictions, and part of the fun in analyzing a superscalar machine is to look at the restrictions on the issue based on what functional units they have, what buses they have, and so forth, and then try to plot out what the execution rate of that machine is going to be and what the pipelines look at. And we'll go through a couple of examples of that. So what are the realities of superscalar machines, since we can't achieve that ideal? Well, one of the problems is that as we reduce the number of functional units, the restrictions on the issue begin to become a significant factor. And in fact, the distribution of instruction types is very non-uniform. It depends a lot on the program. So as you do that, the performance of the machine varies a lot from program to program based on the kinds of instructions and the opportunity to do instruction level parallelism within that program. So the performance of a superscalar machine could in fact have a much higher variance than a conventionally pipelined machine. I mentioned that load and branch delays are now a bigger problem because you count number of cycles and not instructions, and you now have multiple instructions that are being skipped even though you only have a single cycle delay. Branch penalties are a problem. You now may have, if you choose to do it, 3 delay slots for branch. And in fact, doing branch delay slots at all for superscalar machines turns out to be quite a nightmare because it depends a lot on alignment of instructions in pairs or quads and which instructions are in different places in the pairs and so forth. And most superscalar machines, in fact, try to avoid having branch delay slots at all. Well, the consequence is that you've got to do something to make branches take less time. You've really got to do better either compiler techniques or better runtime branch prediction, because as you're executing multiple instructions at a time, the distance between branches in time is getting shorter. You still have a branch every 7 or 8 instructions. That's a property of programs, and you're not going to change that. And you're making those instructions between the branches take less time, so the delay for the branches is a larger fraction of the execution time. The same thing for read after write hazards. They get worse in the sense that each read after write stall is going to cost you multiple instructions rather than a single cycle. The other problem is that there are now lots of hazards to check because you've got twice as many or 4 times as many instructions in progress. There are lots of combinatorial issues of the number of checks you need to make in order to check for hazards. And the result of that is that the whole cycle time of the machine may slow down in order to do those cross-checks. Lots of things can be bottlenecks, including memory as a functional unit. If you combine, which in fact I'll show that some of the latest machines do, multiple issue of instructions in one cycle with dynamic scheduling in order to get things to execute out of order. Remember that for dynamic scheduling, we're using things like reservation stations or reorder buffers where you have to issue or make entries in those data structures in the order in which instructions are issued. Well, now you're issuing 2 instructions at once. you've got to do something. Either you've got to design those units so you can somehow make 2 entries in sequence in those units in 1 cycle time, or you've got to pipeline the instruction issue so that it runs twice as fast as the rest of the machine. So you can make 2 entries into the reservation units, for example, or the reorder buffer in 1 cycle, and then they process things 1 cycle at a time. Or you try to separate them into separate structures. So you could have a separate integer reorder buffer and a separate floating point reorder buffer in order to be able to issue 2 instructions in parallel, 1 each to each of those structures, and have the cycle time of those structures still be the basic cycle time of the machine. And in fact, PowerPC 604 does that, has separate reorder buffers for fixed point and floating point. Yeah?
So that means you restrict the commands that can be next to each other.
That's right. Now, you do restrict the commands that can be next to each other, and many of the machines have those restrictions for several reasons. One is that. The other is the limited number of functional units. Many of them have only 1 floating point pipe and 1 fixed point pipe, so you have to issue 1 of each kind. And if you don't have 1 of each kind, then it stalls. Superscalars are complicated, but they're fast, and this chart just basically shows that most of the manufacturers who are producing incredible advanced microprocessors these days are issuing multiple instructions, mostly 4, in fact all 4 in this case. Even a machine like the AMD-K5, which is in fact an x86 architecture, we'll see can take advantage of superscalar technology, although it's certainly most hard in an instruction set architecture like that. I don't believe any of this line of simultaneous out of order. I was pulling this from different tables, and they were all using different interpretations of what it means to execute instructions simultaneously out of order, so ignore that. Notice that all of the machines do aggressive branch prediction. They all have some kind of branch history table or branch target address counter of anywhere from 256 to 2K entries in order to mitigate the effect of branches, which otherwise would kill the performance on a superscalar machine. They all have multiple functional units, 4 to 10 typically. We'll talk about pre-decode bits a little bit later. Okay, that's superscalar. We'll look at a couple of real machines later. Let's now consider whether or not there's any other opportunities for extracting parallelism besides executing multiple instructions or issuing multiple instructions at once. Well, one way is to try to avoid branches, because branches cause so much of a problem with machines like superscalar machines. And one way is to add predicated or conditional instructions. And this is similar to something we'll talk about in a second, which is speculative execution. Basically having an instruction where you can begin executing it, but in fact whether or not it gets executed depends on a condition which is evaluated, which may be evaluated later. Typically for a sequence like if A equals 0 do an assignment, you would have to do a 2-instruction sequence with a branch around the move instruction which disrupts the pipeline. Why not just define an instruction, in fact, that does that conditional operation in 1 cycle? And in fact can nullify the result of the assignment in the case where the condition should not have been issued. So there are lots of computers that now have this conditional move instruction. I haven't seen any good statistics on whether it's really a great win. It's certainly fun and useful for trivial examples like absolute value and other little examples. But I don't know how often it really gets used by the compiler. It still takes an execution time slot because you may nullify the effect of the conditional move, but it's still taken a cycle. Although I guess you could argue that the combination of branch and move and still took at least 1 cycle anyway, and probably more, so the conditional move is a win. It's certainly a win. Whether or not it's worth the investment is questionable. Nevertheless, most of the modern machines have it. The HPPA RISC actually has a generalized version of it where any register instruction has a bit that says whether the following instruction should be conditionally nullified based on the result of the current register-to-register instruction. That I can see might be, in fact, more useful because it's not limited to just moves, but still is limited to a single following instruction.
Question?
Yeah.
The example there,
Right.
where you have the C move Z, this is just a minor point. Is that supposed to be R2, R3?
Yeah, there needs to be an R3 in there somewhere. Right. So that's one way of getting rid of branches. What's another way of getting rid of branches? Well, we saw some of them before, like doing loop unrolling and register renaming and basically trying to get multiple instances of the loop executing in parallel. But sometimes that's very hard. If you look at a loop like this one, which is a typical kind of list structure traversal, where you're moving down a list, incrementing the value that a pointer points to, picking up a forward link in the list, it's very hard to get much advantage out of unrolling this loop because you can't execute the second iteration of the loop without knowing that the first iteration of the loop is not going to terminate because the null has occurred. So there are lots of loops where getting multiple iterations in execution at the same time is difficult because you don't know that that next iteration is in fact going to occur. What we'd like to do is in fact execute instructions in the second iteration of the loop even though those instructions might not need to be executed or should not have been executed. And this is speculative execution. We've been predicting conditional branches and we're fetching based on the prediction, and in fact we may even begin execution based on that prediction, but now we're going to take that a step further. We're going to fetch those instructions, we're going to execute those instructions, we're going to complete those instructions, and we're going to be prepared in fact to erase them and make believe they didn't happen if it turned out that the branch went the other way than our prediction. Turns out that this works well when you combine it with the kind of dynamic scheduling algorithm that we saw with Tomasulo's algorithm. Tomasulo's algorithm, remember, issues instructions in order. It executes instructions out of order. But now we're going to add another feature, which is that we're going to commit in order. We're going to finish those instructions. We're going to execute instructions even beyond a branch whose direction we don't know with certainty. But we're going to wait to make the final coup de grace for that instruction until we know that the branch has been taken and that all previous instructions have committed and completed. So basically we combine two objects that we've seen before, reservation stations, which we use to get this execution out of order, and a reorder buffer, which we used before to get precise interrupts. Now we use it as well to give us speculative execution, as a way to undo the effect of instructions that weren't supposed to be executed because the branch went the wrong way. So let's look at how that works.
Question.
Yeah.
On that particular example you had, wouldn't you get an interrupt from trying to fetch from a zero memory location?
You would get an interrupt, but in fact, in order to get precise interrupts, and in order to make speculation work right, you have to postpone that interrupt. So in fact, if you execute the second iteration of the loop and you get an interrupt, you basically finish that instruction and carry along with it the record of the fact that it caused an interrupt.
And then you just ignore it.
I'm sorry?
And then you just ignore it.
And then you ignore it because you ignore it if the branch turns out to have gone the other way. Exactly. Here's the structure that allows you to do that. It's basically the same as the Tomasulo algorithm we saw before on the bottom. Operands are fetched from the register file and stored into the reservation units in front of the functional units as quickly as possible, which is to say when the instructions are issued. When the instructions complete, the functional units deliver their result to the common data bus as before, but instead of writing it back to the register file, it now writes it back to the reorder buffer. This is the same kind of reorder buffer we saw before, where instructions are allocated slots in this reorder buffer at the time they're issued. The result represented by that reorder buffer entry, including the value of the destination register, sits in the reorder buffer waiting for the instructions which are before it in time to get to the front of the reorder buffer and commit. We did it before in order to know that there were no exceptions. We do it now so that all of the things before a branch instruction are saved in the reorder buffer. If the branch instruction goes away, we wipe out the reorder buffer entries that represent instructions that shouldn't have been executed. So every time you issue an instruction, including a branch, you put an entry in the reorder buffer. Instructions which complete after the branch stack up behind its entry in the reorder buffer, don't write their results to the register file until the branch is out of the reorder buffer, don't take exceptions, although they're recorded, the exceptions aren't taken until they get to the top of the reorder buffer. So we get both precise interrupts and we get a way of erasing the effect of instructions that shouldn't have been executed.
Question?
Yeah.
Haven't you in this case, though, increased your branch penalty because now you're waiting till the end of the branch?
Yes. In fact, what you've increased by a lot is the misprediction penalty. If you mispredicted and you've got all these instructions here and you're waiting for the branch to get to the top of the reorder buffer to clear out the unexecuted instructions, your miss penalty has gone up by a lot. So in fact, this is another case where you've got to do a very good job at branch prediction. It also turns out that most machines that implement this, like the PowerPC 604, tries to be clever and not wait until the branch instruction gets up to the top of the reorder buffer before it zeroes out the following instructions. And in fact, what it does is recognize that someplace in the middle of this reorder buffer is a branch that we predicted the wrong direction for. Behind that are instructions we shouldn't have executed, and in fact, it then erases the part of the reorder buffer behind that branch instruction and not the part of it in front of it. It's even more complicated than that because I think the 604 allows you to speculatively execute beyond 2 branches. So in fact, the items in the reorder buffer have to be marked with which branch they depend on. So when that branch is finally resolved, it erases the appropriate entries in the reorder buffer and not the ones for branches that eventually did go the right way. As you can see, it gets complicated. One of the other complications is that as instructions are issued, their results now may come not only from the real register file, but from the reorder buffer as well. So there needs to be a kind of associative lookup of the kind we saw for making interrupts precise within the reorder buffer, looking for results which have to be forwarded to reservation stations in the functional unit. Notice now we have at least 3 different places where values are stored. They could be stored in functional units, they could be stored in the real register file representing the instructions which have been committed, or they could be stored in the reorder buffer representing destinations that, or operands that are not yet committed. In fact, one of the homework exercises asks you to think about this and speculate on whether there could be a way of removing some of those redundant copies, and in fact removing the copy of the operand which is in the reservation station. Okay, this is another chart like the ones I showed for the basic Tomasulo algorithm that shows what the data structures are for keeping track of all of the instructions in progress. Let me see if I can remember where we are here. Well, to begin with, this is a load of register 2, not register 6. The instruction sequence we're executing is load, load, multiply, subtract, divide, and add. These 2 load instructions, in fact, have already committed, so in some way they're really out of the reorder buffer. They've written their values back to their final destination registers. The register status doesn't show any destination in progress for register 6 and register 2. And the next thing that's about to happen is that the multiply, which is now at the top of the reorder buffer, is ready to write back its result to its destination register, which is F0. So it can write back its result to destination register F0, clear out the indicator that that reorder buffer number is about to provide the result for that register. Notice that the register status now contains reorder buffer numbers rather than functional unit or reservations, well, functional unit numbers, because the reorder buffer is a convenient centralized place to have recorded instructions and what their destinations are. So what else is happening here? We've got two multiplies stacked up waiting to go. Well, one is a multiply and one is a divide. The source operand for the divide is waiting for a value, which it doesn't have yet, so it's waiting for the value produced by reorder buffer entry number 3. So in fact, as soon as this multiplier writes its result back, it will be able to go. And so forth. I don't want to go through the details of this. This is a description of the rules going from state to state. Notice that in issue, in addition to needing a reservation station slot as before, we also need a reorder buffer slot, and we have to stall if there aren't any more reorder buffer slots available. When we fill in the reservation station entry, we have to copy operands into the reservation station if they're available, and we have to look both in the reorder buffer and in the register file to see whether the operand value is ready. So that's one of the differences between the standard Thomas-Uhl's algorithm and the one with speculation. When the instruction is ready for write back, it writes to the reorder buffer rather than to the register file. And then there's this additional commit stage where when you get to the top of the reorder buffer, you write the register into the final architectural register file and zero the register status and free the reorder buffer waiting for the next entry to go. So similar, but slight modification because of the reorder buffer to allow speculative execution. But now, in fact, we can go beyond probably multiple branches. When a branch occurs, when the branch is originally issued, it puts an entry in the reorder buffer, as I mentioned. It predicts the direction and fetches and begins executing from the path that the prediction corresponds to. When the branch, in the simple case, when the branch reaches the top of the reorder buffer, you basically just wipe out the whole reorder buffer and then start fetching all over again because all of those instructions were wrong. As somebody pointed out, that's a severe penalty to pay for mispredictions. So one of the things to do, as I mentioned, was to partially clear the reorder buffer as soon as you recognize that that branch went the wrong direction. Even more exotic machines, in fact, can begin to fetch and speculatively execute from both directions. I guess I'm not sure of a machine that does that, speculatively executing from both directions. Many machines, in fact, machines as far ago as 25 years ago, were fetching in both directions, but it's much more difficult, and I guess you would need multiple reorder buffers to be able to simultaneously execute in both directions and invalidate either one or the other. As I mentioned, this gives us for free, in some sense, precise interrupts, which is great. Questions? Okay. What I'd like to do now is sort of do a once-over lightly on some real machines that are superscalar machines and try to get extremely high performance. As part of these lecture notes, there are two papers. One of them is a paper, both of those papers are less than a year old. One of them is a paper that compares the DEC Alpha 21064, which the machine I'll talk about first, to the IBM PowerPC 601. And they're very different machines in the style of superscalar they are. The second paper, in fact, looks at the IBM PowerPC 604, which is a machine that, in addition to being superscalar, also does this speculative execution, has Thomas-Uhl's algorithm, and really is the state-of-the-art in complex superscalar execution. Both of those are interesting papers. I encourage you to read them. I obviously don't expect you to understand all of the gory details of every step in the execution of those machines, but to get a general idea for what they include, what the issues are, and what the problems are in getting those machines to operate correctly. But first, the 21064. The Alpha instruction set we looked at a little bit earlier on. It's a fairly traditional RISC design. It's got a couple of funny items. One is that for historical reasons they have to support VAX floating point as well as IEEE floating point. It was a very early 64-bit architecture machine. All its registers are 64 bits wide, which other instruction set architectures are only recently beginning to adopt. It has the conditional moves we talked about. Yeah?
About 64-bit architectures.
Yeah.
Is there any research being done to see whether or not integer registers larger than 32 bits are ever really used?
I don't know if any research is being done. Certainly the push toward larger and larger memory spaces leads us to want to do addressing with addresses which are more than 32 bits. And that's probably the major factor, rather than needing integers which are bigger than 32 bits. Needing addresses which are bigger than 32 bits. And in particular for multiprocessors, where you may have 1,000 machines and 100 or 1,000 times the memory for that conglomeration in a configuration where any machine can access any of the memory. You need more than 32 bits of address. If we have enough time, toward the end of the course, we'll talk about multiprocessors and shared memory machines and all of that. How'd this get here? This is wrong. It does not, as far as I know, have scaled addition for array indexing. It has a very traditional kind of displacement plus register addressing mode. Has some byte manipulation instruction and some clever branch target hints, which are important because the 21064 is in fact a very deep pipeline. It's a 2-issue superscalar machine with a very deep pipeline and a very fast clock. These characteristics are different from the PowerPC implementation we'll see, which tends to have a shallower pipeline, a slower clock, does more in each cycle. They're very different approaches and have different performance characteristics as a result. As far as I know, the 21064 is the only microprocessor ever to have been listed in the Guinness Book of World Records. In fact, that was in 1992, and it was listed as the world's fastest microprocessor. The 21064 has now been superseded by the 21164, which is even faster, so I have a suspicion it can continue to be listed in the Guinness Book of World Records. They use incredibly fast clocks, 200 or up to 300 megahertz. Because of that, they dissipate an awful lot of power. They're very hot-running chips, but they are speed demons. They blaze.
The scaled addition, that's not an addressing mode. That's a combined multiply-add operation, isn't it? And it probably does have that. Yes?
You may be right. Scaled addition for array indexing. Okay, you may be right that it has an instruction that computes this result, but then a subsequent load or store instruction has to use it as the address. I think you're right. There was probably some reason why I put that line down there. But I'm pretty sure that the load and store instructions have only displacement off of a register type modes. The 21064 in some sense is a RISC implementation of a RISC ISA, and the PowerPC is more a CISC implementation of a RISC ISA. They tried to keep, for the 21064, a very simple internal structure. They start with a machine that is a single-issue machine with the functional units it needs, and can issue 2 instructions at once, but only if there are no structural hazards. If those 2 instructions don't use the same unit, and there are basically 4 separate units, really only 3. The branch and the load store in some ways are the same pipeline. But there's certainly a load store pipeline, an integer pipeline, and a floating point pipeline, and if you get the right pair of instructions in your 8-byte fetch, fetches 2 instructions, 8 bytes at a time, aligned on an 8-byte boundary, they can issue an integer plus a load store or a branch or a floating point in one cycle. They can also issue a load store and a floating point operation in one cycle. Some of the other combinations which you think might be able to issue can't be issued because of restrictions on data paths. They have added an additional pipeline stage because these two instructions are fetched and basically wind up at the head of the queues for the pipelines. In fact, let me show the pipeline diagram. This is straight out of the paper that you're going to read. They basically fetch 8 bytes, 2 instructions, and feed them into the beginning of pipelines going down to functional units. If they notice that by swapping those 2 instructions, they could get 2 instructions to operate in parallel, they do that. In fact, I guess even if you can't get 2 to operate in parallel, you still have to execute the swap to get the right instruction to the right path. Now, that's not quite right, because you can, at the issue stage, if they have an instruction in this top pipeline making its way down, at the time that that instruction is issued, in fact, it can be moved to the integer instruction pipeline if it was originally in the floating point instruction pipeline. So this crossover swap is primarily there for the case where 2 instructions are issued, but they're in the wrong order to be executed for the pipeline that they're in the front of. So there's this additional swap pipeline stage, which in addition to swapping also does some additional decode. Issues are always in order, and executions are always out of order. This is not a machine that's doing speculative execution, and they have to stall for read after write and write after write hazards. It's basically a scoreboarding machine, not a Tomasulo algorithm machine. And because the pipelines are deep and they want to eliminate the delays for read after write hazards, there are lots of bypass paths. And in fact, this diagram shows a couple of them, but the paper points out that they did not clutter this diagram with all the bypass paths that exist in the machine. The pipeline itself is deep. For floating point instructions, it's 10 cycles. Even for integer instructions, it's 7 cycles. It goes through instruction fetch, this swap stage, which does some preliminary decode and the instruction swap to get things in the right pipeline that I was describing. Then an instruction decode, then a register fetch. Note that register fetch and instruction decode here are separate cycles. The clock speed is so fast, you can't do too many things in one cycle. So a lot of the DLX-like cycles that we saw combined into one get split into 2. ALU operations get split into 2 cycles. The really simple things get done in a single ALU cycle. The more complicated things, like shifting more than a few number of bits, take a separate second ALU cycle.
Question?
Yeah.
If the registers, I thought register fetching was independent of the decoding, so why can't it happen in the same cycle? Unless the architecture is different as far as the instruction, the way they look.
Good question, which I can't think of the answer for at the moment.
On the Alpha, they're really pushing the clock speeds. So, like on their latest version of this processor, they've got 14 gate delays for every one of the things. And so, my guess is they're probably moving some of that register fetch over a little bit by skewing the clock into the other latches.
Well, but the argument is that if the instruction is ready at the end of instruction fetch, and ID and register fetch can begin at the same time in parallel, how does that gain anything? David says, I don't know. Answer is, I don't know either. One of the things they try to do is reduce the branch delay, because in a deep pipeline, branch delays cost you a lot. So they do, during this swap phase, enough decode to be able to do branch prediction. Let's look, in fact, at some of these sequences in the pipeline and what delays are.
Question?
Yeah.
It seems like they can't do those together, ID, register, fetch, because if they're going down and they're in the wrong channel, they're going to be, they may get their the registers from the wrong register. In other words, if they're in the floating point,
Oh, that's interesting.
they have to go into the other one, and you can see where the line is there.
Yeah. That's an interesting speculation, that in fact they need to decode enough to know which register set they're going to be fetching from. I'll buy that. ALU instructions. Do we have any delay for ALU instructions? Well, basically not. If it's a simple ALU instruction that produces its result at excuse me, at the output of the ALU1 cycle, then they can have a forwarding path that forwards its result into the input of the ALU1 cycle for the instruction executing in the next cycle. Now notice that this is an instruction in the next cycle. There may have been an instruction in between these two that got issued at the same time as this original add to a different pipeline. So there might be a floating point instruction in between this add and subtract that got issued to the floating point pipe at the same time. They obviously are not going to be forwarding to each other because they're using different ALUs and different register sets. In the case of an add and a subtract, since there's one integer pipeline, they could not have been issued in the same cycle, so they are delayed by at least one, and in that case there's no additional ALU delay because they can forward one to the other. If these were both paired in the same instruction pair, then in fact there is, I guess you could call it an ALU delay. It's actually an issue delay because they couldn't both issue at the same time. What about a load instruction? Well, a load instruction is basically done at the end of the write-back stage, and a subsequent ALU instruction that uses that result has to suffer a 2-cycle penalty in order to use that result. Now remember that it's 2 cycles. It may be 2 to 4 instructions, depending on whether there were multiple instructions that got issued in a cycle or not. Now one of the questions is, why couldn't you forward from the end of the mem cycle if that's when the data is really available? Well, that has to do with what this HM means. If you go back to the pipeline stages that show what happens during a load store, in fact, the mem cycle is doing the cache fetch. And we'll talk about this later, probably not today, but next time, that doing the cache fetch is not the last part of fetching from memory. You also have to do a detection, at least in an associative cache, to see whether or not that is the correct value from the cache, or if there are multiple values coming out of the cache, which one of them is the correct value. So in pipelines with longer cycle times, you can combine that in the mem stage. In pipelines like the 21064, where the cycle time is so short, that has to be moved into the next cycle. So forwarding from a load store instruction has to happen at the end of the write-back stage, not at the end of the mem stage.
Is this the same as the R4000's tag check stage?
Yes.
And are there any machines, of these 3 big ones, like the PA RISC, the DEC Alpha, the PowerBC, etc., do any of them not stall on a cache miss?
No. All machines stall on a cache miss, certainly. This is more a question of, in a cache hit, how fast can you go ahead? If the cache misses at this point, you then have multiple cycles of hit. You still can't use the data until the end of the write-back, even if it's a hit. So there are no machines that don't stall when cache misses, because there's not much you can do about that.
Question?
Yeah.
Why doesn't it start doing the ALU op after it gets some memory, and then if it figures out it's the wrong thing, just, you know, shift over then?
Well, I think your question is, why doesn't the ALU proceed with the data that came out of memory, and if it turns out to be a cache miss, you can just invalidate that instruction? Is that the question? The answer is, we'll see later on when we look at caches. The memory may not be producing just one result. It may be producing multiple results, and you've got to check the tags to see which of those to forward into the next instruction. It's not just whether or not it's good, it's which of n values is the right one to use. We'll see that when we look at associative caches. Okay, what about branch delay? Well, in the worst case, where you really have to wait for the result, then the result is computed in ALU1, and the next instruction can be fetched following ALU1. It normally would have been fetched if you did appropriate prediction in cycle 3. So now it's being, well, if there were no branch, it would have been fetched in cycle 2. So if you wait until the end of ALU to fetch the next instruction, then there's a 4-cycle penalty, and that's the penalty that you would pay if you mispredict the branch. So it's a 4-cycle or 4 to 8 instruction branch penalty. And notice that there are typically 7 or 8 instructions between branches, so the branch penalty is severe in a machine like this. They are doing branch prediction as at the end of the swap phase, so in fact predicted branches themselves suffer 1 cycle delay. Yeah.
I guess I don't quite understand that. If you can't get the address you need to fetch, even if you predict the branch is going to be taken, you're still going to have to wait till the end of ALU1, right, to get the actual...
Unless you use things like branch target buffers, for example.
Okay.
Which I don't believe E21064 does, but that's one possibility. Let's look more at branch prediction on the 21064. The penalty is large because of the extra pipeline stages. What they do is to include essentially the equivalent of a branch hit cache by including in the instruction cache a branch prediction bit that says that the last execution was a taken branch. And in fact, they compute the PC relative branch target in the swap stage. I guess that partially answers your question, that they don't wait until the end of the ALU to compute the branch target. They can do enough decoding in the swap stage in order to do the addition of the displacement plus the current PC. But it's still 1 cycle late, so there's a 1 cycle bubble that gets added in the pipeline. Instead of issuing the subsequent instruction here, if they predict in a taken branch, they have to do it at the end of the swap phase. One of the clever things they do is that they allow that delay bubble that just got inserted into the pipeline to be absorbed later on. If there's a subsequent instruction that blocks the instructions behind it, which could proceed into the bubble, are allowed to obliterate the bubble. It's the kind of thing that you didn't do or we didn't do in the DLX pipeline, but delay bubbles can be basically a no-op instruction, and that no-op instruction can be overtaken by an instruction behind it that can proceed. So so it could be, in fact, a 0-cycle penalty. And as I mentioned before, the 21064 doesn't have branch delay cycles because in superscalar machines they're a nightmare. What the 21064 does have for subroutine returns is a stack that the hardware implements that allows it to predict subroutine return addresses. Notice they can do this PC relative target early in the swap stage in the case where it's a conditional branch. They can't do that for a return from subroutine because, just as you were pointing out, you'd have to wait until the end of ALU1 maybe, or at least register fetch before you could do that. So what they do is to have a separate stack, I think 4 deep, that keeps track of subroutine calls that were made, and when they recognize a branch, they predict when they recognize the subroutine return, they predict the target address by popping the top element off that subroutine return stack in the swap stage to try to keep it to a 1-cycle delay. Okay, let's look at I guess we have time to do this, example pipelined loop for the 21064 and try to figure out how it schedules. This is our traditional simple loop of adding to a vector a constant and storing it in another vector. The loop is basically this. We fetch a floating point value, we add the constant which has been pre-stored in register 0. In this case, we're going from the back of the loop to the beginning, and we're making the further simplifying assumption that one of these arrays begins at location 0 in the machine, so that you can test the end just by looking to see when its index register goes to 0. So we do the addition, we decrement the pointer for array A, I guess this is. We do the store, we decrement the pointer for array B, and then branch back to the load instruction based on the zeroness of the address pointer. Well, the first two instructions we can issue simultaneously. They go to the load store unit and the add unit. The load proceeds through decode, register fetch, address generate, memory, and write back. The add needs to stall because it has to forward the result of the load instruction to the first stage in the floating point pipeline. Now this is a machine that could, in theory, is this true? Well, the next stage which happens is it fetches the subtract and the floating point store instruction. They can issue together. One of the rules, though, is that instructions must issue in order. So issue is the point at which it actually does register fetch. Since the add was delayed, the subtract has to be delayed as well. You can, as we'll see here, you can issue instructions together if they've been fetched as part of the same pair, but not if they've been fetched as separate pairs. So the subtract winds up delaying until after the add cycle. They have to be issued in order, except for the fact that they could issue together if they come from the same pair. In this case, they don't come from the same pair. The store instruction gets fetched and decoded simultaneously with the subtract, but it has a read after write hazard waiting for the output of the add instruction. So it waits for the result of the add coming out of the last stage of the floating point pipeline and needs that result for the input of the memory stage. Now notice what's happening here, that in fact the machine pre-computes the fact that the earliest point it could execute the memory phase of this instruction is in cycle 13, and backs up from that to discover when it is it should issue the register fetch. This pipeline can stall in the first few stages of the pipeline, but once it gets into execution, and I think that includes register fetch, there are no subsequent stalls allowed. So in many cases it looks ahead of time at what the requirements will be for forwarding, and then backs up from that to know when to issue a previous instruction, a previous stage of that instruction. That's part of why the bypass logic and the stall logic for a machine like this is very complicated. So now we fetch the subtract and the branch. They, because we issue in order, have to be delayed to issue after the store instruction. They get issued down here. The branch target is computed at the end of the swap phase, and it's predicted taken because there's a bit in the instruction cache that says that this branch was taken last time we saw it. So in fact, instruction fetch can occur in the subsequent cycle. Execution is delayed so that we do instruction issue and register fetch after the instructions that were fetched in the cycle in the pair before it. And at this point we're in steady state, and one way to look at how long the cycle is taken, well, we can look at anything to anything. We can look at the memory stage of this load instruction and the memory stage of this load instruction, and see that the repetition rate is 9 cycles. So we've got 9 cycles per loop in steady state. We've got lots of store cycles, lots of stall cycles, which is what tends to happen in a deep pipeline like this. But a fair bit of parallelism going on nonetheless, including parallelism that represents instructions issued at the same time executing in parallel. This is a case where better software scheduling and loop unrolling, in fact, can be a very big win. And the compilers that DEC provides for the 21064 does aggressive software scheduling in order to make this pipeline run even faster. We're out of time. Next time we'll talk about the PowerPC 604, and then we'll start getting into memory hierarchies.